Okay, I'd like to welcome you to session 3A. And the first talk is an exponential separation between randomized and deterministic complexity in the local model by Yi-Run Chang, Zvi Kopelowitz, Seth Petty, and the talk will be given by Yi-Run.
Okay, so thanks for the introduction. The title of the talk is Exponential Separation Between Randomized and Deterministic Complexity in the Local Model. But this is actually only one of the several results in our paper. So in this talk, I will talk about other results as well. Okay, so the model that we consider is the local model, which is the most classic fundamental model in the study of symmetry breaking in distributed computation. So in this model, the communication network is modeled by a graph, and each vertex is a processor, and each edge supports reliable communication in both directions. And the communication proceeds in synchronized rounds. And in each round, each vertex can communicate with its neighborhood. So in this model, we allow unbounded amount of local computation power and also unbounded message size. And we also assume that each vertex knows the following two parameters. That is n, which is defined as the number of processors in the network, and delta, which is defined as the maximum degree. And the runtime in this model is measured by the number of communication rounds. Okay, so in one round of the local model, an algorithm first each vertex first sends and receives message from its neighborhood, and then it does some local computation. And after the last round, each vertex decides their output independently. And equivalently, we can also view a T-round local algorithm as follows. First, it gathers all information within the distance T neighbor, and it does some local computation and decides its output. The reason that these two definitions of local algorithms are equivalent is because we don't have any constraint on the message size. So essentially, what a vertex can learn in a T-round algorithm is essentially all the information within distance T neighborhood. Okay, so there are two variants in the local model. That is the deterministic version and the randomized version. In the deterministic variant, we allow each vertex to have a unique ID of length big set of log n. This is to break symmetry. Otherwise, what we can do in the local model without IDs, very limited. And in the randomized variant, we don't need ID to break symmetry since they have the randomness. So, but since we allowed randomness, we must tolerate some failure probability. And the standard is to allow the failure probability of 1 over poly n. Okay. So first, we have some very easy observation. It seems that not all problems are interesting in the local model. For example, we can easily observe that all problems can be solved in diameter time, because in diameter time, we can gather all the information and solve it locally. And indeed, there are actually a lot of examples where you actually need diameter time. For example, maximum independent set. And these problems are not considered interesting in the local model because, you need the global information to solve them. So these problems are inherently not local. So you may wonder what kind of problems are of interest in the local model. It turns out that essentially all the interesting problems in the local model belongs to the category of locally checkable labeling. So informally speaking, labeling is locally checkable if its correctness can be checked locally. And for example, the coloring and the maximal independent set, these two are locally checkable. Okay, so before proceeding to our result, let's do a very quick exercise to allow you to familiarize with algorithms in the local model. So how do you compute 2 delta coloring? And there is a very easy algorithm. So first, each vertex holds a set of variables color, and in each round, they just choose one uniformly at random. And let's see. So you can see that the 2 end vertices successfully color themselves because there is no conflict while there is a monochromatic edge here. So the middle 2 vertices will proceed to the second round and choose the color again, and they're done. So how do we analyze the runtime of the algorithm? So observe that in each round, each uncolored vertex successfully color themselves with probability at least 1/2. So after log n round, we will have a 2 delta coloring with high probability. So that's how this algorithm ends in log n time. So in the next, I'm going to present a very useful and very generic tool that allows you to design a randomized algorithm based on a deterministic algorithm. So recall in the previous example, suppose that the allowed failure probability is not 1/poly n. Instead, it is 1/delta. Then the procedure will take only log delta time. So if for simplicity we assume that delta is a constant, then this is constant number of rounds. And what is so good about the failure probability 1/delta? If the failure probability is 1/delta, then the expected number of uncolored neighborhood is less than 1. So we can conclude that with high probability, the connected components formed by the uncolored vertices have size at most O of log n. So suppose that we have a T of n time deterministic algorithm. Then how much time does it take to apply the deterministic algorithm on these connected components? It is T of log n time. So this will give us a randomized algorithm that runs in T of log n time, which is sort of an exponential improvement over the best deterministic algorithm. Okay, so this is the current state of the art in the local model. This looks very complicated, but you can find out that there are some regularity. For example, if you ignore the dependency on delta, so the randomized complexity is actually identical to the deterministic complexity on O of log n size graph. For example, here you can see that there. And what does it mean? It means that essentially all the state-of-the-art randomized algorithms follow the this graph shattering framework Also notice that this is going to be presented in the next talk in this session. Okay, so this just raises a very intriguing question. That is, can we do better than the graph shattering technique? That is, if we denote the det p as the time complexity in that local and rand p as the optimal time complexity in rand local, then suppose that the deterministic complexity is this, then is it possible to obtain a randomized complexity that is much better than this? And surprisingly, we can show that the answer is no. That is, the graph shattering technique essentially gives us the optimal randomized algorithm in the following sense. That is, we prove that such inequality holds. Okay, so before presenting our proof, let's do one more exercise. So you may wonder how a typical lower bound in the local model looks like. And here is a very classic example. So the theorem is that any small O of log delta n time algorithm that colors a tree must use this many colors. The proof is very simple. Because any algorithm that runs in this amount of time cannot distinguish between a delta regular tree and a delta regular graph that has a very high girth and also high chromatic numbers. So if we have a small amount of colors, then it will not only color a tree, but also color this high chromatic this graph with high chromatic number, and this will lead to a contradiction with the chromatic number of this graph. So it means that such an algorithm must use at least omega of delta over log delta colors. So there is a remark that is such kind of lower bound is inherently unable to separate randomized and deterministic complexity. So if you want to separate the randomized and deterministic complexity, or you want to prove a lower bound that is specific to ran local or dead local, then you must explicitly incorporate either the failure probability or the distinct IDs, that is the feature that is specific to these two models. Okay, so let's begin the proof of our first result. Okay, so recall that what we want to prove is this inequality. So our strategy is de-randomization. Suppose that you have a randomized algorithm. Then your goal is to de-randomize it to obtain a deterministic algorithm that meets this inequality. Okay. So our proof will follow the very classic BPP containing p-poly proof. That is, we first find a way to amplify the failure probability, and then so we are able to use union bound to argue that there exists some choice of random bits that will work for all graphs, so that we can de-randomize the algorithm. Okay, how can we amplify the failure probability? So we will just use the definition of the ran local model, because the failure probability that we allow is depends on the size of the graph. So we just add some isolated vertices, and then so the failure probability will increase. So let's define capital N as 2 to the n squared. And 2 to the n squared is much larger than the number of n vertex graphs with C log n bit ID. Okay, so we have already amplified the failure probability. So the next thing to do is to argue that there exists some choice of randomness that will work for all graphs. So let's say that a function phi maps a C log n bit ID to a random bit and to a random string. And we say that a subset of phi is a deterministic algorithm that stimulates the randomized algorithm with the random bits fixed to be phi of ID of v. And we say that this function is bad if this deterministic algorithm fails on some n vertex graph. And if we choose this function uniformly at random, then by union bound, the probability that the function is bad is less than 1, so they must exist a good one. So as long as all the vertices agree on the same good function, we are able to de-randomize it. And the reason that we are able to let everyone agree on the same function is that, well, they can just pre-compute the lexicographically first good one prior to the first round. And also know that we don't have any constraint on the local computation power. So we obtain this inequality. Okay, the first takeaway message. So this inequality can be interpreted as a de-randomization and also a lower bound. And we show that there is such a conditional lower bound in the local model, and it also shows that the graph shattering technique is necessary. So we have shown a conditional lower bound here, and it is another integrating question whether the reverse of such an implication is true. That is, does omega of log n in ran local imply omega of log n in dead local? And surprisingly, in this work, we show that such an implication is true. And in fact, we actually prove something much stronger than this. Okay, so to prove this, it suffices to show this because a lower bound in random local immediately implies the same lower bound in that local. Okay, so the theorem that we are going to prove is this. This is automatic speed up theorem. That is, given any deterministic algorithm that runs in less than log n time, then we are able to speed it up to run in only log star n time. So the implication of this theorem is that there is nothing whose complexity that lies in between log star n and log n. So if you have a lower bound that is between log star n and log n, you automatically get n, log n lower bound. So the proof sketch is as follows. First, we use a technique called linear coloring to reduce the ID length to smaller ones that are distinct within small distance. And then we will run the same algorithm while pretending that the graph is much smaller. So how does it work? Because if you run your algorithm in a small amount of time, let's say in tau time, as long as all the vertices you see in distance tau are distinct, then you are not able to tell whether you are in a small graph or a large graph. So this kind of technique will work. Okay, so let's give some details of the proof. So basically, the runtime of our technique is as follows. First, we use linear coloring to produce small IDs that are distinct within small distance, and then we execute the original algorithm with the new smaller IDs. And we actually set tau as a constant. So the bottleneck is the linear coloring algorithm, which runs in log star n time. And that's why, that's where the log star n comes from. And also notice that this proof will work for all the locally checkable labeling problems. That includes coloring, maximal independent set, maximal matching, and so on. Okay, and this is the second takeaway message. That is, there is nothing that lies in between for constant delta. Okay, so you may wonder what will it like if we allow some non-constant value of delta. And the reason that we care about non-constant delta is because of this table, which shows the state-of-the-art complexity of delta coloring trees. And by symmetry, you feel that the correct answer here is omega of log base delta n. And actually, we are able to prove that this is actually the correct answer by a similar technique. So let's give some details. So basically, what we do is very similar to the previous proof. We use linear coloring. And the technique that we use is a lemma that is called the round reduction lemma that is introduced in the stock paper. So this lemma basically means that you can reduce the number of rounds by 1 at the cost of increasing failure probability. So if the number of rounds of your algorithm is too small, then this will lead to a contradiction because you can just iterate this lemma for t times and you will obtain a 0-round algorithm with some small failure probability. That's impossible. So using this technique, you will automatically obtain this log n lower bound in random local. And if you may feel that if you set p equals to 0, then you will automatically obtain this log n lower bound in that local. But this is not a correct inference because in the dead local, you need to have a distinct IDs in order to execute a deterministic algorithm. And to generate such ID, you need this failure probability. So you still get this log n lower bound, which is not good. But we can overcome this barrier by first generate a very long ID and shrink it using linear coloring. Okay, so we obtain this lower bound, and the combination of these two results will give us the first instance of exponential separation. Okay, so that's it. Thank you.
Is it possible that there are separations above for algorithms that take more than epsilon log n times? Are there these other gaps, or will it be continuous?
So if you apply the same technique on some special graph like cycle, then you get a much bigger separation that is between log star n and n. So yeah.